So today, what we're going to do is talk a little bit about MOSA and how it applies to a lot of the technologies that are central to C5ISR. And as a starter here, Mercury is a company delivers processing technology to aerospace and defense industry through our processing platform, which we're looking at here. The processing platform is designed to offer our customers the capability needed to ensure technological superiority across all domains. In today's battle space, using real time sensor data to make accurate and timely decisions is becoming the key success factor. To process this data in real time, we offer capabilities spanning silicon to systems. However, we also need to ensure our customers are able to rapidly deploy this processing technology. One approach we take in this is alignment with open architecture standards, which brings us to our talk today. We're going to cover how did MOSA originate and how it flowed into the industry, looking at the SOSA organization, and then taking a look at what C5ISR domains and objectives are, and some of the critical technologies for that particular C5ISR, and then take a look at some new direct RF solutions to support it, and then how SOSA supports those initiatives and brings it into a deployable platform. So with that, let's get started and take a look at what the MOSA objectives were. These flowed down from DoD, and in 2019, there was a directive that said all of the services will use open standards to enhance competition, facilitate technology refresh, incorporate innovation, enable cost savings, cost avoidance, and improve interoperability. So these were the government directives, the DoD directives. And what happened was each of the three services, the Navy, the Army, the Air Force, took those major objectives and then interpreted them for their own particular needs for the platforms that each of those services had to provide solutions for. It turned out that a lot of the solutions chosen by each of the three services were very similar. And so they decided to converge into a common SOSA consortium to blend a lot of the different technologies that they had into one standard, and hence the SOSA technical standard evolved. So there's a lot of ongoing continuous development of standards to support new missions and new technologies as they require to to address new threats as they come about. The product of the SOSA group, that main product is the technical standard, and standard .1.0 was released last September not 22 but 1. So it's been almost a year and a half now, and people have been using it. It's a reference that talks about the hardware, software, and electrical mechanical parts of a system. There are over 145 different member organizations in SOSA, and they all contributed to the making of this document. What's going to happen is you're going to see more and more government procurement activities will be requiring compliance or conformance with SOSA going forward as it becomes more and more popular each time. Each time we come around for a new opportunity, a new platform, you're going to see, excuse me, you're going to see more and more reliance on the SOSA as the guiding document of how it's going to be built. So let's take a look at what C5ISR is. Now, these are the operational domains of C5ISR, and you can see the 5 C's up front and the ISR down at the bottom. So these are areas of discipline and technology development. And what they're intended to do is to create technical objective solutions. And these include all the ones that you see here: electronic warfare, command and control, intelligence, operations, surveillance, reconnaissance, counter IED, and so forth. So these are what those different operational domains on the left are applying their expertise to solve solutions for these particular objectives. And taking a look at a lot of those objectives, you'll notice that they have to do with RF signals. EW, of course, is all electronic signals, typically electromagnetic radiation, radio frequency signals, and the C5ISR systems. Many of them also use RF solutions, and they really require a lot of different technologies to now do what is required for today's platforms. And they include artificial intelligence, very low latency, broadband high frequency operation, very complicated signal processing, low swap. And for the phased array antenna that you see over there on the right, you need synchronous RF signal channels to support those elements in a phased array system. So one of the things that has revolutionized RF for these types of applications is called now direct RF. Now, what is direct RF? Let's take a look at a traditional radio architecture. This is the heterodyne architecture, where you had a front end stage that was all analog, and it was a down conversion in frequency from the antenna signal frequency down to a lower IF frequency. That was then followed by the IF sampling stage, where an A to D converter would sample the lower IF frequency. The problem with this solution is all of the complexity of the mixers, the oscillators, and other analog circuitry in that front end made these systems rather bulky. For each channel, you'd need this whole signal chain. What direct RF does that's different is it raises the speed of the sampling rate of the A to D converter, so the A to D converter can directly digitize the antenna RF signal frequency. And as technology evolved, that of course keeps increasing and has increased now to where we're up to close to 64 gigasamples per second to digitize very wideband signals. The real benefit here is that these signal channels and all the RF processing can be done in a very small footprint. And that's critical for a lot of the deployed platforms that we were looking at before. This is a first step into direct RF monolithic technology for EWC5ISR, and this is the Xilinx RFS SOSA chip. And what you see here is you see data converters, A to D converters and D to A converters, that are capable of digitizing signals up to 6 gigahertz in signal frequency. The signals are directly coupled into an FPGA, which can then handle the wideband signal paths that 8 of these channels in and out need in order to support the high bandwidth IO that's required for a particular RF application, whether it's communication or radar or EW. Now, that was a first step, but the sampling rate here is really only 5 gigasamples per second. There are new devices that are appearing now that are pushing this performance level up for what direct RF really means. So some of the new things include new FPGAs, and one of them is the Xilinx Versal AI artificial intelligence ACAP, which is an adaptive compute platform. And this gives you a lot of different pieces that you see here. Adaptable hardware, which is configurable logic, AI engines, DSP engines, and so forth, that can handle different computational needs for very complex waveforms and very wideband signals. So this is the type of advancement that the FPGA technology is pushing in order to keep up with the very high bandwidth data rates that direct RF mandates. We move ahead, you see how that FPGA we just looked at is being combined into a system in package. This is the direct RF transceiver called the multi-chip RFS1140. And what it does is it combines that FPGA we just looked at with 4 10-bit 64 gigasample per second A to Ds and D to As, capable of digitizing signals up to signal frequencies of 36 gigahertz. So this is it's made in a DMA accredited facility here in the US, and it combines all of the data conversion and the FPGA processing all in a single package. There are additional devices out as well, and these include products from, this would be an Intel product, Altera Stratix 10AX, and the Intel Altera Agilex Direct RF FPGA, both using the 10-bit 64 gigasample per second A to D, D to A converter tiles or chiplets that are connected directly within the same package, again, to the Intel Agilex or the Intel Stratix X FPGA to do the signal processing. So you can clearly see that there are multiple solutions already available in the industry to solve these kinds of problems. So how do we take this new technology and get it into a SOSA, an open system architecture platform? Fortunately, SOSA specifies a lot of different parts of the system that include the backplane I/O, different mechanical, different cooling, different connections for RF signals in and out, and platform management. All of these different standards support all of the technology that we just looked at, so we can take those devices and put them on board level products and deploy them rather in a very straightforward way based on using the SOSA technical standard 1.0. The other thing that the SOSA standard specifies are other VITA specifications for backplane analog RF I/O, as well as optical I/O for high-speed optical digital signals as well. It's exactly what you need to handle those types of technology for EW C5ISR. Here are some examples of some MOSA-aligned products from Mercury with different capabilities. You have processors, you have the RF SOC, you have a Versal ACAP Xilinx devices with high bandwidth memory and with the AI core, and just processor boards as well. So there are a lot of products emerging now, and these are just representation of ones from Mercury. What this really has done is then it's taken a lot of what the MOSA objectives and applied it to EWC5ISR. Faster, easier, improved life cycles, reducing cost, and rewarding innovation going forward. So, key takeaways. SOSA membership now includes 145 vendor organizations. The standard is now released. We've got dozens of products out there being used. DoD will start specifying SOSA increasingly in programs of records, and it's really a clear long-term advantage to everybody in our industry. So if you need some more links, here are some links to go for to get to the websites, to get to some of the capabilities that we have here at Mercury, and then also a link to the technical standard 1.0. So anyway, we are here and we're ready to help, and we're very excited to be part of the SOSA organization and open systems in general. So that's it for me.
Okay, I got a question here for Rodger Hosking. Doesn't SOSA make systems more expensive?
No, absolutely not. And I know that's the perception, and our keynote speaker today addressed that quite well. I thought that David Tremper did a good job. Actually, once you get into it and get away from some of the false misconceptions about SOSA, find out that not only can you get systems done more quickly, and time is money in the development cycle, but you can reuse platforms that were developed previously by, having common elements in those platforms and not have to reinvent the whole system each time you want to insert new technology. So I would strongly suggest that a more careful analysis is it does reduce cost, especially over the long term.